Hello again. So for this short bit of maths that you might find useful, we're going to quickly look at two-dimensional polar coordinates. So we've already seen for the Schrodinger equation, if for an atom, the natural coordinate system is spherical polar coordinates in 3 dimensions. But before we do that, let's do 2 dimensions. So here's a cup of coffee that I bought earlier. So the question we want to answer is, what is the length of the circle at the top of my cup of coffee? Circumference, but I can't spell circumference, so I'm going to call it length. So here we go. All I want to do is calculate the length of this circle, the circumference of this circle. So you all know that it should be 2 pi r, whatever distance I got from the center. So you've already used in your mind two-dimensional polar coordinates to solve this problem. You haven't said to yourself, it is something complicated to do with the square root of x squared plus y squared. Naturally, we could write down the equation of a circle like that, but it's going to be horrible. So let's not do that. So let's draw down what my cup of coffee, I forgot to get sugar, looks like. So here are my 2 axes, x and y. And here is the edge of my coffee cup, a perfect circle. All right. So it's got some radius r. And I want to know what the circumference is. All right. So r can take a coordinate 0 to infinity, and I've also got an angle theta, and theta can run from 0 to 2 pi. So it's a different theta to the 3-dimensional one. 0 can run from pi, theta can run from 0 to 2 pi. So let's consider a small element, and let's call it dl. Some small element dl. So if I want to work out the circumference, let's call it big L to keep my nomenclature correct. All I need to do is integrate all my little dl's all the way around the ring. Add them all up, and therefore I will have worked out the circumference. Easy peasy. Except we need to know what dl is. So we'll draw a little picture of a slice. So let's draw this down here. I'm going to exaggerate now. So here is my little thing I tried to draw. So I've got some angle, d theta. Got a distance r, and this length here, this length is my dl. But if this angle is small, I can use the small angle approximation, and this length should equal r d theta. So that should equal dl. R d theta should equal dl. And the small angle approximation, assuming that d theta is small, and you can go away and look up why this is. Sine theta equals theta at small angles, the Maclaurin expansion of sine theta. So now we just need to add them all up. So what is the circumference? For some reason I called it big L. Big L, it's going to now, I have to add up all these little bits. So I want to add up from 0 to 2 pi, or from theta equals 0 to theta equals 2 pi, of this thing, r d theta. So immediately r is just some constant for this particular integral because I'm doing it at fixed radius. There's no radial dependence. So 0 to 2 pi of d theta, which is just r theta to pi to 0, which is just 2 pi r. The circumference of a circle. So you can see that putting the problem into a more natural coordinate system, or the coordinate system that has the same symmetry as the problem. The problem with my coffee cup has got cylindrical symmetry, so we use 2D polar circles. So if you wanted this in 3 dimensions, you'd also add z. But anyway. So hopefully you've probably done most of that. Okay, let's ask the next question. What is the next question? If I consider only the actual coffee rather than the edge of my coffee cup, what is the total area of coffee that I can see? Well, it also describes a circle with a slightly different radius, and all I want to do now is add up all the area inside this circle. So the area now. So here is the edge of my coffee. I'm going to call this big R, just to differentiate it from the other R we had. X and Y. And the question is, what's the total area? So I need a little area of coffee. So let's call this dA. And the area of my coffee is going to be adding up all these little dAs. That's all it is. That's all integration is, adding up bits. Okay, I've got lots and lots of little bits of area of coffee. Add them all up, and that gives me the total area. Easy peasy. All we need to do now is define what dA is, and then we're off to the races. All right, so again, we're going to use this natural language. So I've got R, I have d theta. I now know that this side is r d theta, and I've got another coordinate here, and the length of this is dr. So I'm going to define my area. So that dA is going to be width times height, which is r d theta dr. So that describes the little bit of area of my circle. So now we can add these up. What is the area of my circle? Well, I need to integrate r from r equals 0 to r equals big R. And I need to integrate my angles from theta equals 0 to theta equals 2 pi of r d theta dr, so I can move things around. 0 to big R of r d theta, r dr, and 0 to 2 pi of d theta, which is going to come out as, so this one's going to be 2 pi, and this one's going to give me half r squared times 2 pi, so that's going to give me pi r squared. Pi r squared. Exactly as it should be. So again, by placing the question with the right coordinate system with the same symmetry as the problem, it's fairly easy then to work out what the total area is. Another way to think about this is instead of adding up just this little square, we could add up a ring. So we could take a ring which has got circumference 2 pi r, give it a little distance, dr. So I have a ring which has got area 2 pi r dr, and I can add up all those little rings as a function of r, and that will give me the same answer. It's just like doing the theta integral first and then doing the r integral second. So sometimes you see it as integrating up little cubes, and sometimes you see it integrating up a ring. A ring is just, you've already done the angular integral first to give you your 2 pi r. So that is working out the area of circles.